things. Okay. So if you run, and I'm by the way, I'm toggling cells with L to show you line numbers. All right. So this first cell, what we're going to do is we're going to download the fashion MNIST dataset. Okay. So if I just run the cell, and it might take a while because my system is just starting. It's using ML datasets. It might need to pre-compile something, etc. So it didn't take actually so long in my case. As you run the cell, this line number 2, the training data function, train data function from fashion MNIST, well, under the namespace of, or the module fashion MNIST, returns a tuple where the first element is the training X and the second element are the labels, okay? And the test data does the same. Now, fashion MNIST, just like I spoke about now in the lecture, is just like MNIST, but instead of numbers, we have apparel, fashion, if you'd like. All right. So if we see what fashion, by the way, I can do type of fashion MNIST X. Okay, and you know, in Julia, everything has a type, and it's in this case, it's quite a complicated type. It's a base reinterpreted array, fixed point numbers, normed uint 8. So they're basically only 8 bits for each thing, but it's like an 8-bit valued thing that's then normed and represented as a floating point, and it's in an array of uint ints with 3-dimensional array. Okay. Why 3-dimensional array? Because if you do the size, and you've got, it's 28 by 28 by 60,000. Okay, this is how the data is packaged to us. If you're having trouble running any of these cells, then let me know. This is a small intimate group, so we can deal with these things. All right. So just to see what we. So if I could go for example for fashion MNIST X, I could go for the 24th row and the second column and the 3,535th image. Okay, and this is what I get. Okay, so this type of thing, just to see what it is, type of. It's a fixed point number normed uint 8. So it's basically, again, a uint 8, an unsigned integer 8. So that's a number between 0 and 255, but then represented on a scale 0 to 1. So it's just represented in a nicer way. Of course, this pixel is completely dark, okay? If I would have gone to a slightly different pixel, maybe the 22nd pixel, well, I get a bit of weight on there, 0.02. All right. Stop me at any point if needed. So let's plot this thing. So I'll run this cell. Now, this is one of Julia's biggest problems today, and it's called the time to plot, the first time to plot. Okay, so, and it's off-putting for a lot of people because Julia's compiled. You're running the first time in your kernel and you're doing something very simple, which is plotting. You're saying, hey, use a plots package. And here I'm also telling plots, this PyPlots, just telling plot, please use the Python plotting backend. But I didn't have to do that. I could have plotted with a different backend. Okay, that's what the PyPlot function call does here. Okay, the semicolon just, I could have had it like this on another line, it would have been fine. All right, semicolons just to put two statements on the same line. All right, but you see, this thing is still computing because it's doing it's doing a compilation of the plots package. If I run it again a second time, it will be quicker, and a third time even much quicker. Okay, so just know Julia is still not super responsive for first time use every time you start a kernel. It's a bit of a hindrance, but we could live with it. And what we're doing here is we're plotting this thing, and we're asking it actually to flip the Y, otherwise it won't plot it correctly. We're saying no legend, and we're saying color grays. If I would plot it without color grays, we'd see it as a monochrome image, but it's going to use the default, which is kind of a color scheme from yellow to purple. So that's a bit deceiving. So let's just do color grays. What's this dash thing here that I've highlighted?
maybe a transpose.
Yeah, it's a transpose. So this is an image. Actually, to plot it correctly using this heat map, I need to do both a transpose and a Y flip true. And this column, if you've used MATLAB before, since the fashion image text X is a tensor of 28 by 28 by 60,000, okay, I'm getting everything from the first image, okay? Then if I change this to 2, I'll get the second image, etc. Okay. You guys are able to run this. So in a second, you have a task of your own. A different way to plot this, I'd use the image core package, and then I just I convert the type of this array to an image. I use a convert to image package supplied by Fashion MNIST. Then you actually see pixel by pixel. It's not necessarily a cleaner way to see it, but you actually see what it has. All right, so let's see what this thing is. So the class names, we've already created an array called class names, okay? Class names are mappings from the integers 1 to 10, okay? And indexing in Julia starts with 1, to the classes, you know, I mean, with MNIST, this MNIST digits, it's clear. I mean, you've got the digits 0, 1, 2, 3, 4. You'd have to be crazy to permute the digits when you do the class names, right? But here, the first one is a t-shirt, the second one is a trouser. I don't know what a trouser is. I guess you put on your pants, it's like bottom apparel. Then you got a pullover, a dress, a coat, a sandal, etc. Okay, these are the class names. So this is an array. All right. So if we now look at the labels, let's look at the first label. And in Jupyter, by the way, if you don't know this, go to help to the keyboard shortcuts. Okay, so in Jupyter, you guys probably all know this, but if not, don't hesitate to ask me, etc. You know, I can hit escape and use like A adds a cell above, X deletes a cell, etc. It's kind of like the VI editor. So fashion MNIST train Y is a 60,000 array of integers that has the indices 0 to 9. All right. So if I look at the first element of this array, again, indexes in Julia, indices begin in 1, this is 9, okay? So if I want to see what's the class name of 9, I need to do that plus 1, that's going to be a 10, okay? And a 10 is an ankle boot. All right, so this thing is indeed an ankle boot. So class names at this index is an ankle boot. All right, so we need to do some additions to 1 here because Julia arrays begin in 1, but the labels in fashion MNIST start at 0. Okay. All right, so here's your task. Present the second image of the training set. So go ahead and try and do that. And let's take about 3 minutes for that. So it's 3:13 in my time. Let's do it till 3:16. And go ahead and pop some questions as they come about. Okay, and we've got somebody still waiting for the time to plot. I'm sorry about that. Go ahead and try and code your solution to task 1 in parallel as that is happening. Okay, so the task is present a second image, return a second. And plot is also taking as well for others. So yeah, it's doing a first-time pre-compilation. Yeah, the whole Julia community knows about this. That's did somebody plot actually so far? So this is my okay. So we have some successes coming from Adelaide. That's good. At least be comforted that while you're waiting a long time for the plots, if you're doing stuff that's code intensive, Julia will be super, super fast. So almost all of the packages created in Julia are created using Julia. Whereas our friends now in the parallel classes in Python and R, they are running code that's written in C and Fortran because Python and R are not fast enough to create the native code that they're using. So they're interfacing using Python, but a lot of the libraries are written in a low-level language. Julia alleviates that problem. And the first person that was still waiting for the plot, did you get your plot?
I might actually still be waiting for it to download the data set. I'm not sure, but it's okay. I don't mind if you continue.
All right. Any further questions or additional? All right. So let's see if the data is balanced. Okay. So let's look at fashion MNIST. If you remember in the lecture, we looked at MNIST. It was sort of balanced. So here, let's use the stats-based package. Okay. And yeah, so first time you're using these packages, you're incurring even a bit more of a waiting penalty because Julia is pre-compiling the packages the first time. So if we look at the counts function, okay, so counts gets a number and says the number of occurrences we get, right? So if you do counts of the array 1, 2, 2, 2, 3, 4, 5, it's going to give us 1 appears 1 time, but 2 appears 4 times, and 3, 4, 5 each appear 1 time. Okay, that's kind of what counts does. So if we look at the fashion MNIST train Y and do counts, and we see that the data is actually perfectly balanced. Okay, so your next task is just to do this for the test labels. Okay, so remember the fashion MNIST is just like MNIST, so the length of the test labels, I'll just look at the length of the test label. No. There are 10,000 test labels. Okay, so go ahead and look at how many images are in each test label. So how many t-shirts, how many trousers, how many pullovers, how many dresses, how many coats, etc. Okay. So again, this is straightforward. It's counts of the, oh, sorry. Yeah, fashion and mistest. Okay, so you probably did this. So there are exactly 1,000 labels in the test. Okay. Any questions so far? Okay, so I think some of you, when you're running this the first time, it might have opened it had std in input and you had to click a Y, right? Did anybody get that? So when you're using ML datasets, you're actually downloading from a URL the first time you're creating this, and then there was a question, do you want to download it? And you should hit a Y and then enter.
Yep, that one.
Yeah, okay. So that incurred a bit more delay. Sorry, I cheated. I did that prior. So that's kind of the the package downloads a data set from some URL and puts it on, well, in a good place, and later on it doesn't need to do that again. All right, so let's look at the MNIST data set now. Okay, let's leave fashion MNIST and look at MNIST. So what we do in line number 1 is just like fashion MNIST, we just use MNIST. Okay. By the way, keep in mind in the lectures I didn't use the data from ML data sets in the lecture. So let me just show you the code in the lecture. I used it from Flux. Okay, so you've got 2 sources at least for MNIST. I'm not sure if Flux has fashion MNIST. I don't think it does. But just so you look at this. So this was an alternative way to get the data, and it actually it returns the data in a different way. Okay, so the format is not this 28 by 28 by 60,000 tensor when you use Flux. Okay, so this is an alternative way to get MNIST, but Flux I don't think has fashion MNIST. Okay, so Flux is the Julia machine learning library that we'll be using later on in the course for Julia purposes. All right, so this gets the MNIST train X and Y, the MNIST test X and Y. The nice thing is that the MNIST and fashion MNIST are directly replaceable. Now, this at, does anybody know what this at is in Julia? Let's just see if people have used Julia a bit. What this at thing? What is it? What does this mean?
Does it send stuff to the command line or something, or?
No. Okay. So this is, that's fine. So this is these are how macros are activated and specified in Julia. Okay. So when you here, this is the size function as you would expect, but there's also the show macro. Okay, in a macro, you don't need any brackets before or after the arguments of the macro. So macros are just like functions, but they're actually running at pre-process time, not at compile time. Okay, from a user perspective, it doesn't matter much, but it's just kind of a different construct that we use. If one day you create a macro, then you'll see. Okay, so this is a show macro. Okay, so show, just the nice thing about the reason it's a macro, it actually takes the expression which you have here, which you wrote in code, right? This is code, size, digit, MNIST train X, and tells you this thing equals, and it prints it. Okay, so it's very useful for debugging, right? But you see that, you know, it's when you write a program, typically the programs in Julia are compiled. They're compiled to LLVM, and that's low-level virtual machine. It's kind of a general language, a general assembly-like language that's CPU agnostic. And then an LLVM compiler compiles it to your machine, Mac or Windows, or well, to the CPU that you're using. Okay. Of course, the compiler, when you do that, you typically, this is not something you can refer to in the program. Size of digit MNIST train X, that's exactly what we do, right? But with a show macro, you can do that. So here, show of 1 plus 1. You see it says 1 plus 1 equals 2. It actually took the way that we formatted this expression in the program. If you do that, it show 1 plus 1.0 equals 2. All right? So it's, anyway, a lot of words for show. All right, so it tells us this is the size of that and the size of that, and this is the first digit is a 5. And well, indeed, it looks like a 5. All right. So let's look at MNIST. At the counts, we already saw this in the lecture. Okay, but we see this again now. We see that MNIST is not perfectly balanced, but like fashion MNIST. And if we look at the training set, again, we see it's not perfectly balanced. So it's close to balance, but it's not perfectly balanced. These cells here, of course, are markdown cells, and these cells here are code cells. You probably know this from Jupyter. By the way, it's the same in the interface that Sarat is using now for Google Colab, also has code cells and markdown cells. Markdown is a formatting language where you write like this, and you can use things like that for heading, etc. The nice thing about Markdown is, of course, you can write LaTeX inside. Well, it's not the basic markdown, but in all these markdown environments, so then you can, sorry. So you could format nice formulas as well. Okay. This is LaTeX. Okay. Let's see if the data is balanced. Fine. Let's go here. Is it the same for MNIST? Yes, it is. Okay, so let's now do a very rough comparison of the training set and the test set. Okay, now in this rough comparison, what we'll do is let's just compute the mean intensity of each digit. Okay, so what do I mean by the mean intensity of each digit? So let's look at like the first digit. Here it is. This is the first digit. Okay. It's a 28 by 28 array. Okay, that's the first digit. A lot of zeros, but there's a digit drawn in there, right? That this is this 5 that you've seen. Okay, we're actually seeing these positive pixels here. These are like these guys here. Okay, and then this doesn't plot the whole digit. So of course, I could have summed all these numbers and divided them by 28 by 28, which is 784, and that's like the mean of this digit. Or I could have used the mean function on it, which would be the same thing as summing the entries and doing that. Okay, so that's a mean. Mean also comes with a statistics package, so it might be that the different version statistics package might add more methods to the mean function. So in Julia, by the way, every function, so a function is this is mean, this is a mean function, but it might have multiple methods, and you can do methods of mean, and that is, it's not like methods which are methods of a class in Python or C# or Java or C++ or Swift or whatever. It's rather the methods of the function. The function is a basic entity, and the function mean can work on different types. You see, there are 10 different methods for the function mean. You can do mean on different types of things. You can do mean on abstract arrays, you can do mean on static arrays, etc. After I include statistics, is a built-in package, or use statistics. Oh, I thought I'd get more methods from mean, but I didn't. Okay, this is maybe that's it. So every function has many methods. That's all I wanted to say. All right, so here what we're doing is what is this construct called, this type of thing, which I've highlighted? I can also write an example.
I think with looking for extra mean methods, you've already run using means using statistics below, so it's already loaded the extra ones in.
Exactly. Yeah. Thanks. Thanks. Perfect. What is this construct? Do you know a name for this type of thing? Maybe from R or Python or Julia?
A list comprehension or
Yeah.
comprehension?
Yeah. Perfect. So that's a comprehension, which I probably misspelled. Comprehension, probably still misspelled, but let's live with that. Okay. So here we have a comprehension of the mean. But what we're going to do is we're going to now select, this is quite slightly more involved, we're going to select from the digits train X, we'll take all the X coordinates, that's this, we'll take all the Y coordinates, but we'll only select the points where the Y equals K. Okay, so this dot in general in Julia is broadcasting, but it also means when you have some vector here and you want to compare it to a scalar. Okay, so just what we're doing is like 1, 2, 3 dot. I cannot do equals 3. That's, oh well, I can, but that's not what I wanted. So yeah, the thing on the left is not the thing on the right, but I can create this, and then I'm going to get a false, and a true. Okay, so we're going to now, and the second thing we're doing here is we're actually then putting this list of booleans as indices to the third entry of the tensor. Okay, and we'll compute the mean of all of those images. So now it's mean doesn't just work on an array, it works on this tensor. Okay, and what we're getting is a mean pixel intensity for the digit 0, for the digit 1, for the digit 2, etc. Okay, and you'd expect them to be different because different digits require different amounts of ink. Okay, and here is the mean of the test. And let's just plot against the digits 0 to 9 the mean of the train, call that label train, and plot exclamation mark. In general, exclamation mark in Julia is not part of the language. This is just the plot exclamation mark function. This is the name of the function. But the meaning of exclamation mark means that you're actually modifying something. In this case, you're actually modifying the current plot. But just so you know, I mean, look at the function. For example, there's a function sort, and there's a function sort exclamation mark. So sort exclamation mark sorts in place. Okay, so that's a naming convention coming from Lisp, from the old language of Lisp. Okay, so sort exclamation mark is sort the vector in place. So if you actually give it a vector, it's going to, you're getting a reference to that vector, it's going to sort it in place. Just so you know where this exclamation mark comes from. So here the plot, second plot, just adds to the current plot, because if I do this, if I won't have this exclamation mark, oh, maybe I didn't run everything. Mean, yeah, I didn't run this mean test. So I didn't run this. Okay, so we just see the mean. This is just a test, right? Whereas the other plots and adds to it. That's like in MATLAB, I think what you'd call hold on or something funny like that. All right, so this is a bit of a silly way to just compare the train set and the test set and see that their means are roughly similar. This is in no way a rigorous thing. Okay, so try to reproduce the same type of plot here for fashion MNIST. Okay, so compare the mean pixel intensity per digit of the training set and the testing set for fashion MNIST. You should already have the fashion MNIST in memory. Okay, so this is just for you to copy a few commands and play around with it. Okay, so that's task 3. So let's meet in 3 minutes for task 3. So if I write a variable, if I write a few things and hit tab, of course I get auto completion. In my case, I actually made a mistake, and now it's hung. I need to kill it. So stop the kernel. Because this is one of the things that happens with heavy operations. I mean, this is not super heavy, but if I make the mistake I made is doing a whole lot of comparisons, becoming very heavy. Did anybody get it?
Yep.
Great. Well, I'm still here in with an unresponsive page. That's wonderful. Okay.
What was the mistake that you made? I didn't see it.
Yeah, let's, okay, so look at my code. Okay, the kernel appears to have died. I'm happy the kernel died because we want it dead. We can restart the kernel. Yeah, so these things happen, but they do. So so here what I did is I'm comparing the train X, which is this complicated tensor, to K. So the number of entries here is by 784 bigger than what I would have had if I did the right thing, which is test. So this is actually a huge Boolean array. Now, I'm not sure what happens when you put in an array a selection with a Boolean array that's bigger than the array, but I guess I got a bounds error. But just even doing this comparison might have taken a bit of time. Anyway, this should have been test, and then everything would have been okay. But in my case, I restarted the kernel, so I need to run this again. And probably just this. I need to do running plots again as well. And things should be okay. Any questions or? Okay. Not something like that. All right, so the next thing we're going to move on to, I'll finish this in a second, is linear classification. Okay, but let's do binary linear classification, not linear classification like we had in the lecture, which was more complicated than binary. It was multi-class classification. So in the lecture, what we did is we took many binary classifiers. Well, we took 10 binary classifiers. Each one is, you get kind of this inner product of beta and the image, and we chose the one that's maximal. That's a one versus rest classification. Okay. In our case, let's do, okay, let me just run this. That should be okay now, I hope. Let's compare a digit 3 versus a digit 8. Okay, so we'll take our data set. What we're doing here in this cell is we're taking our data sets and we just care about digits 3 and digits 8. Okay, let's call digit 3 being a positive thing and digit 8 being a negative. I still have some mistake here. Let's see if somebody can help me find it. Fashion MNIST train.
I think the second argument in your means fashion train statement should be fashion MNIST train underscore Y. So the one above that.
Oh, yes.
And it should be train instead of test before it, I think.
Great. And then thanks a lot. All right, good. So let's hope that works. Thank you. So positive train, what we'll do with positive train is we'll take the digits and we'll only select the ones that are 3. We'll call those positives. Okay. And just a while, I might probably want to adjust. Okay. So did you guys get something like this type of thing that I'm getting here?
Yep.
All right, thanks. All right, good. So let me also just run this code, which will reload the MNIST dataset because it hasn't been loaded because I restarted the kernels. Okay, and we want image core, sure, why not? That should work. All right. So we have here, these are the positive images. The number of positives is n pos, it's just the size. Now, positive train is a tensor, 3 tensors, so we'll get the third coordinate. That's the number of images, number of negative. Okay, so we got, these are the positive images, these are the negative images. This is roughly a balanced binary classification problem. Okay. Now, what we can do is we can, from each image, we can create a vector. We can use the vec function. Okay, that's also a function that kind of exists in MATLAB, etc. So all the matrix type functions have a similar interface to MATLAB roughly. So if you do vec of a matrix 1, 2, 3, 4, this is like the matrix 1, 2, 3, the matrix 1, 2, 3, 4. You'll get it. You'll get 1, 3, 4, 2. So it's in column major. Okay, that's the default of how vec works. We don't care really if it's in column major or row major. And float 32 just takes these entries and converts them from this 8-bit type of thing to 32-bit integers. And this dot is called the broadcast operator. Dot is the broadcast operator. That's what this dot does. Okay, I didn't run positive train. Maybe I didn't run this. Okay. So this creates a vector for an image. An image is a 784 vector. You see here mostly zeros because it's zeros around the side. Okay. So what we're going to do now is we're just going to take these 784 images and we're going to connect them to each other, one after the other, after the other, after the other. There's 6,131 of them. Okay, so this is going to be this temp pos. Okay, the vcat function does vertical concatenation. Sorry, let me fix. For each one, we're going to actually transpose it. So we'll transpose it. Okay, that's this transpose. And then this is going to be the first image. That's a vector of the first image. That's a vector of the second image. That's a vector of the third image, etc. Okay. So the features are going to be, this first feature is like the first pixel, this is the second pixel, this is the third pixel, up to the 784th pixel. And sometimes when you work with such kind of data, it doesn't hurt to just plot it to see what it looks like. So when you plot it, you'll see this heat map, of course, you'll see a lot of dark and you'll see some sort of quote unquote periodic behavior because you've got a lot of pixels that are dark and pixels just appear pretty much in the middle. Okay, so this is part of our data matrix, which is the positive data points, still without an intercept. Again, the important thing to remember is each thing that I'm highlighting, this is an image, and this is an image. Okay. Now here we'll take all the negative images. All right, so it's the same type of thing, just with negative train. Okay, and the number of negative images is 5,851. All right. And let's also just create a ones column. This is going to be for the intercepts or the bias. Okay. So the number of real features that we have here is not 784, it's 785. So there's 784 pixels and a bias. That's like the beta 0 in simple linear regression, the intercept term. Okay. Now, this is what you'd call the data matrix. In statistics, equals a design matrix. Okay. So it's going to be a HCAT. HCAT is horizontal concatenation of a ones. Okay. That's these ones. Okay. That's this column of ones. And then you're going to put the positive and the negative below that. Right. So the first, how many are there? The first 6,131 rows here. This first 6,131 rows are for positive examples. And the second or the latter 5,851 rows are for negative examples. Okay. And this is really the design matrix. You can actually, if you do a heat map of this design matrix, you can see that pretty much in the middle after you go from the positive examples to the negative examples, okay, there appears to be a bit of a slight shift. Okay, so even when you look at it like that, you see that those guys above look slightly different than the guys below. I mean, you see this kind of change point, or at least if you have a good imagination and a bit of faith. Okay, so what's going to be the response for this? What are going to be the whys? All right. So the whys, what we're going to do in this case, this is slightly different than what we had in the lecture. I mean, yeah, okay, if you reviewed the code in the lecture, okay, the code in the lecture had kind of arbitrary images, so they're +1, -1, +1, -1. So +1, -1 is kind of appearing in a sense of in an arbitrary way. But here we first put all of the positive examples, then all of the negative examples. So we want to fill all +1, +1, +1, +1, +1 for the positive, for n pos. Again, n pos is like for 6,131. And then for n neg, which is again this number 5,851, we want -1, -1, -1, -1, -1. Here you're just seeing the end of the vector. Okay, so we've set up a least squares problem where this is a design matrix. Okay. And this is a matrix A, and we're looking for a vector beta such that A times beta, beta is 785 dimensional, and y minus A beta squared is minimal, minimizing sum of squares. And the pseudo inverse is times y is the solution to this minimization problem. Of course, when we do deep learning, we're not going to do this per se. We're not going to actually use a pseudo inverse like this. It's going to be iterative methods, okay, using gradient descent and variance thereof, which you can also use here. But here, A is not so big, so you can actually just compute the pseudo inverse. Okay, other questions about this? I mean, it's quite involved, but not super involved. The thing is to view how the matrix A is constructed. A has all the ones in the left. You can't see the ones here because it's just too thin, okay? And then has each row is an image, okay? Is in first all the positive images and then all the negative images. And then your y's are all positive ones and negative ones. So if we want to solve this least squares problem, of course, we can have used stuff like maybe I didn't know this. We could have used stuff like GLM, you know, generalized linear model package or something like that, but just solve it directly using linear algebra. So apply the pseudo inverse to y and you get this beta. So this beta, this 785 vector, these are all effectively zeros here. Okay, there are some non-zero entries, is a vector that minimizes this least squares problem. Okay, just to see the entries of this vector, they're mostly 0. You've got some positive ones. You've got some very big one here towards the end. This is like some very important pixel. Okay. All right. So how do we, this was actually the process of training. So after we've done that, how do we classify? Well, classification is simple. Classification is simple. All you need to do is you need the inner product of this vector beta. Oh, by the way, in Julia, if you want to do a beta like that, or any character of interest, you know, you want an epsilon, do epsilon and hit tab, okay? Or do eta and hit tab, or in our case, beta and hit tab. Okay, that's how you get this beta. So you can call the variable beta directly. All right. So the classify, this is a definition of a one-line function. This is a function that gets the argument x and returns something. Okay, so what it's going to do is going to be do beta times the vector, the vectorization of x. X can be a vector, you know, an image if you'd like, but you want to add to it 1. What is this 1 for? Or I shouldn't say add, but rather concatenate a 1 or prepend a 1 to it above it. What is this 1 for?
That's the bias term.
Exactly. Perfect. That's a bias term, just like you had here. That's this one here. So it's exactly implementing this thing without the argmax, because in this case, this is just binary classification. This was a 1 versus rest classification in the lecture. Okay. So that's what it's doing. And if, for example, you now try to classify the first image, we got a positive one. Okay. and try to classify the first image of the positive train. Okay, if we try to classify the first image of the negative train, we get a negative one. Let's try the second image of the positive and the second of the negative. So this is good classification, right? So the positive, we've already split. These are all the positive train are already positive images. Okay, they're already images, which in our case are the digit 3. Okay. Okay, so let's now evaluate the accuracy of this thing, or the performance, I should say, of this thing. So I'm just running a bit over time. I'll finish shortly. All right. So what we can do is we can create, we'll do that on the test set. Okay, so the positive test and the non-positive test and the negative test and the negative. Okay, so again, in test set, we don't have an order of 6,000 images per digit, but we have an order of 1,000 images per digit because there's 10,000 images in the test set. Okay, so what I can do is I can classify here all of the images in the test set. Okay, so I'm going to do it for image 1 through 1010, and I'll check if it's equal to -1 to +1. Okay, and then so this is like this is what, let me just show you this thing without the sum. All right, just look at this comprehension. So we've got, some were zeros, some were zeros, many were ones. The number of ones, the total number of ones that were there we'll just sum them, 968. So we'll count the number of ones. So 968 out of the positive images were positive. Well, ideally, we would have had all 10,000, 1,010. 968 were positive. Okay. Similar for the negative, we'll look at the negative ones and we'll see how many are negative ones. 934. And at this point, what you want to do is you want to actually compute the accuracy, precision, and recall. Okay, so you want to, once you have the true positives, you can also get the false positives, and you can get the false negatives, and you can compute these. So what I'm going to do, I'll finish the session. I'll do this myself, and I'll push this new version to GitHub. Okay, and I suggest that you try and do this yourself. So try to compute the precision, the recall, and also the harmonic mean. Okay, which is the F1 score of the precision and recall. So you'll see this in GitHub. And then try to do it also for the digits 0 and 3. So I'll push the answer onto GitHub. Now, the final thing that we didn't reach is dealing with a CFAR10 data set. And the CFAR10 data set had train data and test data, but in this case, every image is a 32 by 32 by 3, okay, because it's RGB. So there's a bit here of working with these RGB images and then computing the red component, the green component, the blue component, and even this code here that creates an animation of those images and shows the labels. So try to run this as well, and I'll just be available in the consultation hours to answer questions. But you'll see the solution also to task 6 here, which was basically just to process the CFAR10 dataset. Are there any questions or thoughts, or comments?
No, all good.
Okay. All right. So thanks everybody, and sorry for the few technical errors. So you'll see this online, and you'll also see this in GitHub. Just to be clear, just before I finish, when I say GitHub, you can just go to, for example, if you go to the main course, the intro page, and you go here to this GitHub repo. Okay, so unit 1 is what we had in the lecture, but there's a source code for the lecture, but practical unit 1, you'll see the solution pushed into there. All right. Okay, so enjoy tomorrow when you meet with Benoit, and thanks everybody. Bye-bye.